Everyone, in today's class I'll be discussing Lagrange's mean value theorem, which is continuation of the application of derivative which we have started with the rules theorem. In rules theorem you have taken the continuity part of the function differentiability, and then you have assumed that at the extreme points functional values are equal. Then there will be a point, at least one point, where tangent will be parallel to the x-axis. In Lagrange's mean value theorem, it states the same way. I mean, first two conditions will be the same, but the third condition, like f equal to fb, is not there. Okay, so you can see this graph. This is the graph of this dotted one, means it is the curve which is continuous between 2 points a and b. You can see that we can trace the curve. We can join these dots to trace the curve without raising pen or pencil. The function fx here is continuous in AB. This is the first condition. Second condition is fx is differentiable in AB, and there is no third condition. Like in rules theorem, if we have taken f equal to fb, this we are not going to do. But rules theorem proof I did not give you. The proof doesn't bring any extra maturity in your mathematical ability. That's why proof was not given, and proof is not required for entrance examinations. But here in Lagrange's mean value theorem, I would like to give you the proof of the theorem, because the technique you will learn in proving the theorem, which will help you to understand solving from this topic. Okay, so before I do this, I complete the statement part. Then fx is the function, fx is continuous in AB, closed interval, fx is differentiable in AB. Then there exists one or more points C between A and B, this open interval, such that f dash C will be equal to fb minus fa by b minus a. What all this means? Let us consider this graph of the function. This point is a. Coordinate of this point can be taken as a comma fa, and this point coordinate can be taken as b comma fb. Then you can see that there is at least one point where the chord, this is the tangent and this is the chord, AB is the chord, it will be parallel to tangent drawn at that point. Okay, this is geometrical meaning of Lagrange's mean value theorem. Geometrically you can understand easily by drawing tangent over there and by drawing perpendicular on the x-axis here. From A we have drawn the perpendicular here. Then suppose this chord will be meeting the x-axis at a point where the tangent makes an angle phi. Then this tan phi will be equal to, here also this tangent also, if we produce at the point x equal to c, that if you draw a perpendicular here also, draw perpendicular, draw this perpendicular also. Now AL is the perpendicular from here, CM is the perpendicular drawn here on, suppose this is AR and this is PS. From the point A and B we have dropped perpendicular on the x-axis. Now if this angle is phi, this one going to be equal to phi, and then slope of this chord AB is what? This is equal to tan phi, all of you know. Slope of the chord AB is tan phi. And here, what is the slope of the tangent? Slope of the tangent by definition is f dash c, that is dy by dx at x equal to c. This is called f dash c. Now, the angle made by this tangent will also be equal to fb minus fa by b minus a. that is clear from the diagram. If you take it parallel, then this angle phi will be there also, this phi, and tan phi geometrically means what? That is f dash c. So if we compare this tan phi and f dash c, they must be equal. And what is the value of tan phi in terms of this graph, this curve of the function y equal to fx? Tan phi going to be what? The slope. This point has y coordinate fb and this point has y coordinate fa. So tan phi is fb minus fa by b minus a equal to f dash c. So slope of tangent will be equal to the slope of the chord AB. This is geometrical meaning of Lagrange's mean value theorem. There is one point in the graph it is shown, but there may be more than one point. Point may be there also. So once more I just repeat this part. If there is a function fx, it is continuous and differentiable in such a manner that we can draw tangent at every point on the curve. Then between 2 points of the curve where functional values are not equal, obviously fa not equal to fb, there you will get the tangent is parallel to the chord AB. That proof can be given with the help of Rolle's theorem here. So I'll give you the proof I told you earlier. Proof is required, proof is important here to understand the problems will be asked in future to you. Okay, so to prove this, I'll remember the Rolle's theorem. It was continuous in AB, fx is differentiable in AB, and Rolle's theorem there was another condition, fa equal to fb, but here the condition is not given. But if we wish to use the Rolle's theorem condition here, then on the function fx we cannot use, but we will assume that it can be used on another function which we are going to construct. So to give you the proof of Lagrange's mean value theorem, I will be taking this function fx together with another function, say a linear function a into x, and we redefine another function phi xa. This phi x is equal to fx plus ax. So what we are assuming there, let a function phi x be such that phi x equal to fx plus ax, where ax is a linear function, it is continuous and differentiable everywhere. Fx is also continuous and differentiable everywhere we have assumed. So their sum will be continuous and differentiable. So if I say that the function phi x is continuous in AB, phi x is differentiable in AB, and I am implementing another condition on phi here, and let phi a equal to phi b. Also let, this is one condition on phi x, this is the second condition on phi x, and let phi a equal to phi b. Then what do you observe for the function phi x? On the function phi x, Rolle's theorem conditions are useful. I mean, all the conditions of Rolle's theorem can be used on phi x. It is continuous in this, it is differentiable in this, and we brought forward another condition, that is phi a equal to phi b. So third condition of Rolle's theorem also satisfied. Since phi x satisfies all the conditions, since phi x satisfies condition of Rolle's theorem, so we can put phi dash c equal to 0. C is a point in between a and b where phi dash c equal to 0. What does this mean? So 0 will be equal to f dash c plus a into 1. If we differentiate, then the value of a is coming to be minus f dash c. Okay, but phi a equal to phi b, it gives some information about a. Let us put phi a equal to phi b on this function. Since phi A equal to phi B, this will implies FA plus A into A, FB plus A into B. So this implies A into A minus B equal to FB minus FA by, no, that value of A if we find, it will be FB minus FA by A minus B. Now if we substitute the value here by keeping minus outside, this is FB minus FA by B minus A equal to minus F dash C. Therefore, F dash C going to be FB minus FA by B minus A. Okay. So, derivative at x equal to C, which is tangent of the slope of the tangent drawn over there, then they are going to be equal. F dash C is FB minus FA by B minus A. So this condition we wanted to prove by using the conditions of Rolle's theorem. In many sums we are going to see in future that Lagrange's mean value theorem has lot many assumptions like this to prove. Or lot many assumptions means those assumptions must be wrong, must not be wrong, must be correct. They must obey the conditions of Rolle's theorem or Lagrange's mean value theorem. First, we will consider about Lagrange's mean value theorem. It will obey these two conditions, and then there we will get this thing. For proving, sometimes we use that additional condition that phi A equal to phi B, which will help you to get the value of A over there. So we will find applications over there. Before finding those kind of applications, let us see Lagrange's mean value theorem, how it can be used for proving some problems like this. They have asked you to verify Lagrange's mean value theorem for this function in 0, 2. So for this function fx, you all can see this is polynomial function. Solving number 1 here, fx is continuous in 0, 2, and number 2, fx is differentiable because it is polynomial function. Again, due to the same reason, fx is differentiable in 0, 2, and by Lagrange's mean value theorem, by LMVT, we can say that there exists C in the interval 0, 2 such that f dash C, what are A and B over there? A is 0 and B is 2. So there it will be f2 minus f0 by 2 minus 0. All of you understand? Therefore, f dash C is equal to f dash C. If you find for this function, f dash C will be what? Let us find f dash C. The value of f dash C will be what? Fx is given over there, that is x cube minus x square minus x plus 1. So f dash x will be 3x square minus 2x minus 1. Now f dash C going to be what? 3c square minus 2c minus 1. And what is f2 here? You substitute x equal to 2 over there directly. 8 minus 4 minus 2 plus 1. That is 9 minus 6, 3. And what is f0? f0 going to be equal to 1. Just substitute there. 3 minus 1, that divided by 2 minus 0, that is 1. Therefore, 3c square minus 2c, you take this on the left side, minus 3 equal to 0. Now let us find the value of C by using the condition, by using that Sridhar-Acharya method. The value of C going to be equal to 2 plus minus B square minus 4AC, 4 into 3 into minus 3 by 2 into 3. So this thing going to be 2 plus minus under root, this is 36 root 40 by 6. So 2 plus minus 2 root 10 by 6. So let us see whether any one of these two values, that is 1 plus minus root 10 by 3, 1 plus root 10 by 3 and 1 minus root 10 by 3 belong to the interval or not. Root 10 approximately 3 point something. That plus 1, it will give you 4 point something. That divided by 3 is 1 point something, which will lie in this interval 0, 2. And what about the minus sign? No, because 1 minus root 10 is a negative quantity that is not belonging. So since you will write this way, since 1 c equal to 1 plus root 10 by 3 belongs to the interval 0, 2, so LMVT is verified. Now there is another kind of application you can see here. Find a point on the curve where the tangent is parallel to chord joining the point A10 and A21. You can do this thing by using the concept of coordinate geometry and a little bit of algebra. But here the concept is, better, I'll say better than the concept you got in coordinate geometry or algebra here. So let us apply that one, the concept of Lagrange's mean value theorem for this also. You can see that the curve is given, it is quadratic, it's a polynomial curve. Polynomial functions are continuous and differentiable here. So there is no problem of using Lagrange's mean value theorem here. The first condition is satisfied, second condition also satisfied. Now, there must be a point, according to Lagrange's mean value theorem, there must be a point where tangent will be parallel to the chord joining A and B. But one thing you have to make clear, that when you consider the function fx, then the values of x matter. Y also matters, that when you are finding functional value there. So when you are going to do some like number 2, you need to consider the interval 1, 2. So we consider the function fx equal to 2x square minus 5x plus 3 in which interval? In the interval 1, 2. You take it a closed interval, this 1, 2. So this is a polynomial function and interval is 1, 2. Without any hesitation you can say that fx is continuous in 1, 2. Fx is differentiable in y2. Why? Because fx is a polynomial function. This polynomial function must be continuous in this interval, it must be differentiable in this interval. Now, there must be a point in between 1 and 2 by LMVT. There exists C in the interval 1, 2 where f dash C going to be equal to f2 minus f1 by 2 minus 1. What is f dash C? F dash x you can find easily, that f dash x will be 4c minus 5. F dash C. F dash x is 4x minus 5. This is 4c minus 5. So 4c minus 5 going to be equal to f2. f2 is what? f2 will be 8 minus 10 plus 2. This is equal to 0. And what is f1 over there? 2 minus 5 plus 3. So unfortunately we say that here the condition of Rolle's theorem is satisfied. Whatever, you just put it there. 0 by 1, 0. Therefore C equal to 5 by 4. The point you got, this C means the x coordinate. This is 1.25. And if you put xc equal to 5 by 4, the point you can get easily, because they ask you to find the point. You should not give only the x coordinate, the y coordinate also required. You put x equal to 5 by 4 in the given function. If you put x equal to 5 by 4, y going to be 2 into 25 by 16, this plus 3. Take 16 as the LCM, so it will be 50 minus 100 plus 48. This is minus 1 by 8. So the point going to be 5 by 4 comma minus 1 by 8. You must check it once whether I am doing any mistake over there or not. But this is the method. Now let us see what another kind of sum may be there from Lagrange's mean value theorem. This concept is very useful. I told you earlier that while proving, I have assumed that if the second function phi x equal to fx plus ax, so why that you will understand for this kind of sum. And concept of Lagrange's mean value theorem is very useful. See, for this sum we are going to compare these two differentiable functions fx and gx. Fx and gx both are differentiable in the interval 0, 1. f0 is given, g0 is given, f1 is given. Then your problem is to find there exists a number c in between this such that f dash c equal to 2g dash c. Now for our sum, that value of f dash c also that such that f dash c equal to 2g dash c given, they ask you to find g1. How will you start for this sum? Now for these two functions, if we use separately the conditions of Lagrange's mean value theorem, the function fx is continuous and differentiable in which interval? That is 0, 1. For both f and g, continuous here. In 0, what happening? Both fg are differentiable over there. So there exists a point for the function fx such that f dash c will be f1 minus f0 by 1 minus 0, and g dash c will be what? g1 minus g0 by 1 minus 0. Now let us apply the condition here. Since f dash c equal to 2g dash c, so we can put their conditions here. What about f of minus 1 there, f of 1 over there, that you can see f of 1, and just put the value of f dash c first. F dash c is what? That is f1 minus f0 by 1 minus 0, and this is 2 into g1 minus g0 by 1 minus 0. Now what is the condition of f1 here? f1 you must substitute. f1 is 6. 6 minus 2 by 1 will be equal to 2 into what is g1, that we don't know, but g0 we know. We substitute there, so this will give us the value of g1. So g1 going to be what? g1 going to be equal to 2. So this can be determined by just from comparison on fx and gx, and the comparison that condition they have given. So by putting f dash c and g dash c separately, because they both obey the condition of Lagrange's mean value theorem, we can get the value of g1. Now let us consider another type of condition, another type of problem in LMVT, which will help you to understand whether Lagrange's mean value theorem everywhere applicable or not. Applicability of Lagrange's mean value theorem, as you have seen before, it depends entirely on continuity and differentiability of the function. If it is continuous in an interval, if it is differentiable in that open interval, then there is a point where f dash c will be fb minus fa by b minus a. We are able to find the point that I have shown you. But applicability, basically when you are checking, you need to check the continuity part of the function. That function is continuous or differentiable, that you check first. If it is continuous or differentiable, you can definitely apply the condition of Lagrange's mean value theorem. So this is just one function I have taken into consideration, fx equal to mod sin x on 0, 2 pi. Can I use, suppose there is another problem here that fx equal to the same as Rolle's theorem, fx equal to mod x. Can I use Lagrange's mean value theorem over the interval minus 1, 2 for mod x? No. Fx is not differentiable at x equal to 0, so Lagrange's mean value theorem can't be used. Can I do it for fx equal to mod sin x? Mod sin x, all of you know how to plot. First plot the graph of sin x, and from there mod sin x can be plotted. If we take the graph of mod sin x, then it appears like this. Just the upper half will be there, lower half will be removed. It's like this. Okay, so this point 0, this point pi, this is 2 pi, this is 3 pi, 4 pi, like this. They asked you to get it from in the interval 0, 2 pi. Can I use? No, because at the point x equal to pi, the function has a kink. Mod sin x has two types of tangents over there at the point equal to pi. Pi plus 0 one kind of tangent, pi minus 0 another kind of tangent. Okay, at this point tangent will be like this, at this point before pi tangent will be like this, and they are not giving you the same value of dy by dx. So the function has a kink at those points where it is equal to 0, at 3 pi, 2 pi, 4 pi, 5 pi, wherever you see. They are asked you to find at the point 0, 2 pi, in the interval 0, 2 pi. This pi is lying in this interval where it is continuous but not differentiable. Since fx equal to mod sin x is not differentiable at x equal to pi, so LMVT is not applicable here. Okay, so you have seen simple application of Lagrange's mean value theorem, where you can find a point in between two given points, tangent will be parallel to chord. You have checked the applicability of Rolle's theorem, and you have seen that when two functions comparison given there, then how to find dx. Many applications are there. I am going to discuss one by one. Next session I am going to explain some inequalities with the help of Lagrange's mean value theorem.